I'd like now to talk about the iodoform reaction. Now, the iodoform reaction is useful for creating carboxylic acids, and it's also useful for identifying methyl ketones. When a methyl ketone reacts with the iodoform reagents, which are iodine, potassium iodide, potassium hydroxide, with the second step of H+, what we end up with is a carboxylic acid and this yellow compound called iodoform. This is a yellow solid, and it's very easily identifiable. You see it come out as a solution, so you know you've got a methyl ketone. If a non-methyl ketone is used instead of a methyl ketone, the kinds of compounds we get from the same set of reagents have iodines attached to the carbon next to the C double bond O, and these compounds are typically yellow oils and not yellow solids, so we can easily identify methyl ketones when a yellow solid pops out of solution. Turning to the mechanism, what we're looking at here is in the first step, OH negative takes hydrogens off the carbon that's next to the C double bond O. These hydrogens are somewhat acidic because the anion that they form is stabilized by resonance with the C double bond O on the adjacent carbon atom. Each of these hydrogens is fairly acidic and can be removed with OH negative. Once the H has been removed and we're left with a negative on the C, it can attack the iodine in a nucleophilic type displacement and take the iodine off, take one of the I's off the iodine molecule. That leaves one I attached to the C. The process can be repeated twice by removing these two hydrogens and replacing each of those with iodines as well. Once we get to this step, the O negative can come in from the OH negative and attack the C and push the electrons up onto the oxygen. This leaves an O negative which comes back down and then kicks out this group here. Kicking out a carbon group is not something we see very often. In fact, it's a fairly rare process. Other groups can be kicked out, but groups with carbon tend not to be kicked out because the anions are usually too unstable. In this case, though, we make an exception, and the reason we can do that is because of this kind of thing. What's happening is that we have three iodines attached to a carbon connected to a carbonyl group. What this does is it has two delta pluses right next to each other, and we've got these three iodines here as well. These are big atoms, and what this does is it makes this bond particularly long and therefore particularly weak. And if this bond is weak, it means it can be broken. So the way it works is that the OH negative can now come in, push the electrons up onto the O negative can come down, and then kick this C out because this bond is very weak. It comes off as a C negative. The C negative is still not particularly stable, so it will rip a proton off the resultant carboxylic acid and will do so in quick order. After it does that, we can throw in the H plus in the second step, and the O negative can take the H plus, and we end up with our carboxylic acid. And there's the iodoform there, which will come out as a yellow solid. A common question I get is, why does the C negative take the H off the carboxylic acid? Why don't we simply add the H plus from the second step to the C negative and form the iodoform that way? Well, the reason we do this is because the C negative is less stable than the O negative. The other way of looking at this is that carboxylic acids are first and foremost acids. That means that the H plus is very easily removed by a less stable negative charge than what we're going to get after the H plus has left. And that's what's going on here. So the C negative will take the proton off the acidic carboxylic acid, and then the O negative will take the H plus that we add in the second step.